Okay, here we go. Thank you everyone for coming, and thank especially to Aaron Naber for giving this lecture. Just a brief introduction. Aaron is a professor at the Northwestern University, New Horizons Prize in Mathematics for 2018, and Fermat Prize in Mathematics for 2023, so, serious guy. And today is going to talk about the structure of singular set and energy identity for harmonic maps. Whenever you want.
Thank you. First, thank you very much for the invitation, and apologize for the virtual appearance. Apparently, tornadoes in Illinois and workers in Germany don't mix well. So the purpose of my talks today and tomorrow are to give sort of my own little personal celebration of Milan by discussing works that are joint with co-authors in the Milan area. So I haven't given this talk before, which typically means that when time runs out, I'll kind of just quit, because that usually means that I haven't quite timed it right just yet. So we'll see how this goes. And additionally, I tend to like to draw pictures on a blackboard next to the screens here, because it just makes it a little bit easier to visualize. And since I clearly can't do that, we'll do our best to try to make this work. So, okay. Today's talk is going to be joint work with Daniele Valtorta. I'm going to be discussing some new and old results on the blow-up behavior of solutions of nonlinear harmonic maps. The basic outline of the talk is going to be the following. First, we'll talk a little bit about harmonic maps and introduce what they are. Then we'll talk a little bit about singular sets and stratification for nonlinear harmonic maps. This is a somewhat useful conversation anyway, because the setup here is very similar to the setup in a lot of kind of modern nonlinear geometric PDEs. I mean, so Yang mills or minimal surfaces or Ricci curvature or whatever you like. I mean, you have a very, very analogous sort of setup in all of these things. They of course have their own nuances, but so any complicated definitions that you learn here, that will kind of apply to other areas. And then we'll talk about the main theorems. So on the structure of singular sets, this is an older theorem that Daniele and I have. And my thought was to give a proof outline for it, but actually very likely I will skip that, because I want to make sure that I have time to actually discuss defect measures and the energy identity, which is the newer result that we have. And with a little bit of luck, actually discuss a proof outline for this. So our maybe a little bit of background to begin with. By the way, please stop me if there are questions while we're going along. So consider a mapping F from some ball on a Riemannian manifold into another Riemannian manifold, right? And then the thing you can do about that, I mean, pretend like it's a smooth mapping, whatever. Then you can look at its derivative, right? And its derivative is gonna map the tangent space at x to the tangent space at f of x, and it's gonna be a linear mapping, this derivative. And being a linear mapping, and given that this is a Riemannian, these are both Riemannian spaces, we can look at the norm of this linear mapping, right? So that's what this norm is here. It's the norm of this linear mapping here. And then you can look at the norm squared and integrate the thing, and this is your so-called energy function. And when we say that F is harmonic, it can mean one of three things. And the important point to observe here is that these three things are all the same in the linear case. When this target N is just R, right? They're all the same thing, but they're all quite distinct in the nonlinear case. So the first thing it can be is what you call weakly harmonic. So it solves the Euler-Lagrange equation. So that is, if you're a critical point of the energy functional, you're going to get out of this thing an Euler-Lagrange equation the way you kind of normally do, and that's going to be this guy. And so we could ask for our F to just be a, an H1 mapping that solves this weakly, and we call such a thing a weakly harmonic map. The other thing you can be is a stationary, which, there's actually a slightly more complicated definition, but for all intents and purposes, what you're really saying is that it's a critical point of the energy functional. It's quite subtle here, the fact that being a critical point of the energy functional is not the same as solving the Euler-Lagrange equation. They're clearly the same thing in the case where the mapping is R. And in fact, if this is a harmonic map happens to be smooth, they're still the same. But in the case where this is just a weak solution, if this isn't a smooth solution, they may not be the same. It turns out that there are types of directions you can vary F in that aren't captured by this. If you're not smooth, you can't put them together right. This turns out to be the more important condition, the stationary. Somehow being a critical point is more fundamental than solving the Euler-Grange equation. And the last thing is you might be a minimizer of the energy function. So you know, that usually means with some fixed boundary data or whatever you're going to do. But you're a local minimizer. So any other F that agrees with your guy outside of a compact set or something has to have larger energy. And once again, this is not the same thing as being a critical point, which is not the same thing as being weakly harmonic. But we do have that in general. Being a minimizer does imply it's a critical point, and that does imply that it's weakly harmonic. So we do have the implications going this way. So it's getting stronger as we kind of go down the list in terms of what we mean. So just to give some sort of background and regularity of theory of all these things. So the regularity theory of a harmonic map depends on what notion of a harmonic map, how strong it's a harmonic map in all this case. And there are examples by Tristan that tell us that if you're a weakly harmonic map, you can actually be everywhere discontinuous. So these things can actually be fairly horrific in terms of their regularity theory. But on the other hand, if you're a stationary harmonic map, so if you're a critical point of the energy and functional, then you will at least be smooth away from a set of codimension 2. This is a result of Bethuel. So there's a big distinction now between being a critical point and being weakly harmonic. Solving the equation isn't the important thing, being the critical point is. And minimizing harmonic maps are actually smooth away from a codimension 3 set. This was actually the first real regularity theory that got proved, and it was proved by Shane and Uhlenbach back in '82, if I recall. And there's a nice old conjecture floating around, the codimension 3 conjecture, which actually says that these stationary harmonic maps, which we know are smooth away from a codimension 2 set, so that's like a point in a plane, or away from a plane in a higher dimensional space, are actually smooth away from a codimension 3 set. So just like the minimizing case. This is a very subtle and very hard conjecture. The reason for the subtlety is that in the stationary case here, unlike the minimizing case, you can blow up on codimension 2 sets. So you aren't effectively smooth away from a codimension 3 set. That happens to be the case in the minimizing. So analysts aren't very good right now at proving regularity theories that aren't effective. So we'll see this a little bit when we talk about defect measures, about how things can blow up on a codimension 2 set, and yet the expectation is that you're smooth away from a codimension 3 set. So some sort of technical definitions that are going to kind of float around here if we want to talk about this. So our sort of first real question here is what do that singular sets kind of really look like here if we're going to talk about singularity? So we already sort of distinguish between smooth points and non-smooth points. The theorem that we sort of said that the regular set can just be where your stationary or minimizing harmonic map is smooth, and then we have everything else. And so what does this everything else kind of look like? And there's a variety of refinements to the answer to this question. But a good place to start is to talk about blowups and tangent maps for all of this. So the rough definition, which again, these sorts of definitions actually appear for all these regularity theories for any of these equations that might float around in Yang-Mills or something like that, is the following. So take a mapping, right? At this point, it can be whatever, right? It's a mapping from some ball into some other Riemannian manifold, let's say. Then, no, I have two definitions at once. I didn't mean that. Okay, so take a point X in our space. Oh dear. Here, take some ball of radius R, like so. And then we want to sort of microscope on some small little ball around a point. And to do that, what you're going to do is basically rescale your function f. Your f sub x r here becomes a mapping, instead of from the ball of radius 2, it's a mapping from roughly the ball of radius r inverse. Around the origin, by simply translating x to the origin. So I'm sliding this point to the origin, and I'm going to rescale this ball of radius r to a ball of radius 1. So I'm basically microscoping up on my ball there, and we call this a blow up at that point in that scale, right? So it lets us sort of zoom in on it. And we call f sub x, so no r here, a tangent map at some point x floating around here. If there exists a sequence of scales getting smaller and smaller, r sub j going to 0, such that when we keep kind of zooming up at smaller and smaller scales, we get a limit, and that limit is f sub x, and so we call that a tangent map, right? So this thing is basically like the small scale behavior of our function. Pop quiz, which maybe doesn't work so well because it's a little bit hard to communicate with you guys this way. If I can stare you down, I can sort of force you to answer this. So the first sort of question to think about here is if you've got a smooth mapping here, right? What it's say smooth at a point even, right? So it's smooth in some neighborhood x. What is this tangent map of f at this point x, right? And the incorrect answer that one sort of oftentimes says until you look at the definition carefully is that it's the derivative, and that's not the case. What it is remember, you're just zooming up at this point. There's no rescaling of it, just zooming up. So what that means is that if you're just continuous even, what you should be is a constant at that point, namely just the value of your nope, there we go, great. You should just be a constant. So namely the value of f at the point x at that point when you zoom up more and more. Quick remark here. So these definitions here are really for any function f, but of course what we're interested in here are, say, stationary harmonic maps. And a question might be simply that, is this a reasonable definition to take? I can always, of course, rescale a map, but how often will it actually converge at a point? And for a stationary harmonic map, right, as opposed to minimizing one, I might say, it is the case that for every sequence r going to 0, there is a subsequence at least for which you get convergence to a tangent map. So tangent maps do exist. They exist at every point. At this point, whether or not they're unique is kind of an open question. Other contexts out in the world are actually not unique, but here it's an open question. Let me just sort of make a remark, which I won't sort of spend too much time on in just a minute, which is that these limits should not just include the L2 behavior of the convergence, they should include something called the defect measure, but we'll return to this for sort of the second part of the talk. Okay. So if we have an idea of what blowups and tangents are, so infinitesimal behaviors of our function at a point, the next notion you really need to understand in order to understand singularities and how we decompose them is the notion of symmetry. So in a tangent map f doesn't need to be a constant. Like if you're continuous at a point, it'll be a constant. If you're smooth at that point, it'll be a constant. But in general, it doesn't need to be a constant. Classically, one stratifies the singular set based on how many symmetries the tangent map has. So to try to say this in words a little bit, the idea is that you're going to split points up, not just based on whether it's smooth or singular, right? I mean, that's kind of maybe what you're interested in, but you're going to try to do a more refined job of it. You're going to split points up based on how singular points are. And the crux definitions here are going to be symmetries. That's what I determine for you how singular a point is to make it precise. And this is the clutch of kind of modern regularity theory. To prove effective estimates on equations like this, the way you tend to do it now is that you'll take your solution. You'll first prove that at most points and at most scales you have a lot of symmetry, or at least a lot of almost symmetry. And then you will also prove that if you have enough symmetry, you're actually smooth. And when you put these two things together, you end up getting effective estimates on how often you're smooth. And you'll get even effective estimates if you do it very carefully, right? So this notion of splitting things up by symmetry here is sort of how you prove that. Actually, it's the only way to prove estimates right now for equations like this. So let's get some definitions in. So I need to define for you. So we've defined infinitesimal behavior already. That's the tangent map at a point. Now I need to find symmetries for you. So take a mapping, which will be from Euclidean space Rn and to n. I visualize this as being a tangent map at a point, right? Because when you zoom up on a manifold more and more, it just becomes Euclidean space. So it's a mapping from all of Euclidean space. And we first say that it is zero symmetric if it's radially invariant, right? So that means that the value of the function, it really only depends on the value on the sphere, right? If I take its value here, or if I take its value here, it's the same over each ray, right? So it's dilation invariant. It doesn't depend on it only depends on the value on the sphere when you project into it. So we call that zero symmetric, radial invariance. And we say it's k-symmetric if it is radially invariant and it's invariant by some subspace, V, right? So the picture here is something like, okay, that's supposed to be a subspace, not a very good one, right? So if I have a function from my Euclidean space into R, and V is some k-dimensional subspace, so you know, x-axis or whatever you might want. We'll call it k-invariant if it's invariant if it's radially invariant, so it actually only depends on the sphere here. That's zero symmetric. And if it's invariant under translations by this V sub k. So it actually only depends on this sphere of dimension, not Sn minus 1, but Sn minus 1 minus k. You've lost all the k translations. So it's actually a function of a very small dimensional space in this case. So as just sort of mentioned, a k-symmetric function can then be identified with a function on the n minus k minus 1 sphere, right? So it only depends, the radial invariance of the sphere, and the k-symmetries knock out most of that sphere, and all I tell you is that smaller piece that actually matters. For everything else, you can just get it by translation or scaling. And that's symmetry. So basically it's saying your solution, which is n-dimensional, actually looks like a solution which is on n minus k minus 1 dimensions, right? So you've basically thrown out dimensions by your symmetry. And again, stop me if there's questions. I have a feeling if I was in person, people would stop me with questions.
No worries, I will.
All right. Okay, 3 basic examples to kind of consider here first that are somewhat instructive. First is just the constant. So a function here is n-symmetric if and only if it's a constant, right? So if you're a function from Rn into a space, and if you're invariant under some n-dimensional subspace, translation by an n-dimensional subspace, well, there's one n-dimensional subspace, that's Rn. That means you actually don't depend on any point, you're a constant. As silly of an example as that sounds like, that's actually quite important, because what we already kind of did was we related regularity to whether or not the tangent map was a constant. And in fact, the converse will be true too, right? So if the tangent map's a constant, you'll actually be smooth in a neighborhood of that point. So now what we've done is turn tangent map equals constant, the way you would be for a continuous or smooth function, into symmetry. So if you have maximal symmetry, then you have to be a constant, and we'll see that that'll force you to be smooth. To see an example where you don't have maximal symmetry and something non-trivial is happening, consider the following example. Consider the mapping from R3 into S2, which projects onto the 2 sphere. So it's something like this, right? Each point X projects down to its value on the 2 sphere. So this function here is clearly smooth, but not at the origin. Right. At the origin, there's no ill-defined. I mean, it's ill-defined. So this is a zero symmetric function, right? It doesn't depend on the radius at all. It is in fact a harmonic map from S3 into S2, a nonlinear one. In fact, it's even a minimizing harmonic map from R3 into S2. Note that the singular set of this guy is exactly codimension 3. So like with Schoen and Uhlenbeck's result, do that. Here we go. Like with Schoen and Uhlenbeck's result, we expect that singular set to be codimension 3. This is the prototypical example, right? So with this minimizing harmonic map from R3 to S2, the singularity set is just the origin. That means codimension 3, a point in R3. Note as another interesting sort of point here, if I look at the tangent maps of this guy itself, right? So if I take some point in R3 and I zoom up on it to look at tangent maps, then I have basically 2 options. If I don't take the origin, which is where you're singular, right, then you're smooth, and therefore the tangent map's a constant. On the other hand, if I take the origin where you're not smooth, well, you're radially invariant. That means that when I blow up a ball of radius r, I just get f again. Nothing changes, even for the finite blowups, much less the limit. So in this case, actually, my blowup is f itself, which is clearly not smooth. So at least in this context, we see that tangent map equals a constant corresponds to being smooth points. Tangent map not being a constant corresponds to singular points. And again, that's actually a general phenomenon, said correctly. And finally, one more example. This is basically the last example, but just in higher dimensions. So let's consider mapping from Rn into S2. And what I'm going to do is I'm going to split my Rn into an Rn minus 3 cross R3, and I'm going to ignore the first Rn minus 3 variables. So if I do that, then I'm again going to project to the 2 sphere inside of my R3 here, so y over the norm of y. But now instead of being 0 symmetric, you're n minus 3 symmetric. So this is sort of, again, the prototypical example of n minus 3 symmetric guy. It's again going to be a minimizing harmonic map. So you're invariant by the Rn minus 3 translations. You're invariant under radial invariance. And you're minimizing harmonic map. And in this case, the singular set's not a point, right? The singular set's actually all of Rn minus 3. So it's n minus 3 dimensional. Okay, so with a little bit of luck, we're hanging on because I think the last of the bad definitions sort of coming up. Actually, maybe just to make a quick point real quick. So if I consider different setups, like minimal surfaces or Ricci curvature or whatever, Yang-Mills, you do almost exactly the same thing. You're going to define symmetry and split stuff up based on symmetry. The definition of symmetry will be different in each, right? So they each have their slight nuances in terms of what actually represents symmetry. However, there is a definition of symmetry in each that's sort of the natural one to pick, that can be controlled in an almost completely analogous way that it gets controlled here. So for a stationary harmonic map, we're going to decompose the singular set of f, so the set of non-smooth points, based on symmetries of the tangent cone. So how symmetric the infinitesimal behavior at that point is. And the definition here for us, which comes from Federer originally in the minimal surface context, is the following. For a stationary harmonic map, right from some ball into to another manifold M, we're going to define the kth stratum of the singular set to be, okay, it's a double negative definition, and this is subtle and kind of important. The set of points X, for which no tangent map, that should be map, no tangent map is k plus 1 symmetric. Let me say this in words that are a little bit better. What you want is this SK to be the k-dimensional part of the singular set. What you want is this SK to be the set of points where the tangent maps are k-symmetric. You want them to look k-symmetric. That way you have this sort of k-dimensional aspect to your points. Instead, the way it's initially defined is through those points which are not k plus 1 symmetric. And this was initially a deeply clever definition by Federer. What it allowed him to do was, since no one knew uniqueness of tangent anything, no one knew that just because one is k-symmetric doesn't mean the other tangent maps are k-symmetric. He defined it through this sort of contrapositive definition of looking at points which aren't two symmetric. They're not k plus 1 dimensional. What we'll actually see, the results that Daniele and I have from a few years back, is that you could actually now define it in terms of those with k-symmetries, right? But this is really an after-the-fact point that requires quite a bit of work. It's almost more or less equivalent to having kind of manifold-type structures for these things. Just to sort of go back to the examples from before. So in the second example, this was the mapping from R3 into S2 by projection, right? The singular set was just the origin. And to be more precise, it was S naught, because that tangent map was 0 symmetric. It was just the mapping itself, but it's not 1 symmetric. and therefore it is in the S naught part of it. So as sort of one would predict, it's zero dimensional based on this. And for the example 3, which is where you ignored those first n-3 variables and then projected the last R3 onto the 2 sphere, the singular set was just this Rn-3 plane, which is n-3 dimensional. And again, they're all n-3 symmetric, those tangent maps, but none of them are n-2 symmetric, right? So that is, again, Sn-3. It's a very kind of healthy exercise to unwind the definitions and make sure that it all matches up with what you expect it to match up. Okay, so let's now talk about some known results on the regularity theory of minimizing and stationary harmonic maps. So the first results I really want to kind of go through are those by Shane and Uhlenbeck in 82 and Bethuel in 93. Shane and Uhlenbeck mainly focused on the minimizing case, although actually what they did really works for the stationary for certain aspects anyway. And Bethuel really improved a lot of the results to the stationary case later. So the setup is the following. Take a stationary harmonic map, so that's like a critical point of the energy functional from one Riemannian manifold into another. Then, as you would kind of hope from a stratification, the dimension of the kth stratum of the singular set is indeed at most k out of this, right? It could be empty, right? So it could be less than k, but it's at most k inside your space. It's worth pointing out that what they did here, so results like this go back to Federer, where he did this in the minimal surface context, and basically all proofs of these sort of dimensional estimates on stratifications are exactly Federer's. But what they found that let this work was a monotone quantity. They were the first people to write down that there's a monotone quantity for these stationary harmonic maps. And then once you had that information, then they could plug in this sort of dimension reduction machinery of Federer in order to prove results like this. And they did better, right? So this dimensional estimate here, what it allows them to actually do is that in the minimizing case, they're able to prove the singular set was just the n-3 stratum, right? So that's basically to say, an equivalent way of saying that is that once you have n-2 degrees of symmetry, once you have too much symmetry, you actually have n degrees of symmetry, you're maximally symmetric and therefore smooth, right? So there's that gap. And this sort of gap phenomenon is also kind of standard. And that means that the singular set is actually bounded by this top stratum, the n-3 stratum of the singular set. And so the dimension of the singular set is at most n-3. In the minimizing case, they prove this. And what Bethuel did really was to improve this to the stationary case. Bethuel's real contribution here was to prove an epsilon regularity theorem. So once you have enough symmetries, once your energy is small, he was able to prove you're smooth. Which Shane and Uhlenbeck did in the minimizing case, but doing it in the stationary case is actually quite subtle. So this is great, these sorts of estimates, but the question becomes, what kind of structure do we have on the singular sets? So we know they're k-dimensional from up here. The kth stratum is k-dimensional. However, there can be a lot of this. This is Hausdorff dimension. This is a pretty wild thing. This can be all kinds of Cantor sets. This can be dense. This can be all kinds of craziness a priori, right? So our expectation from just the basic pictures that we draw and maybe hopeful reality is that these k-stratums should actually have much more structure in that. They should basically look like a k-dimensional manifold. Like in the context of our minimizing example before, our n-3 stratum for our projected example, the singular set was just Rn-3, right? It was a nice plane. Right? We should hope for some sort of manifold structure on this sort of thing. Although, let me point out that the correct replacement for manifold here is something called k-rectifiable. K-rectifiable basically means, you could have crossings like this, so that would be like a one rectifiable thing, because maybe that middle point isn't a manifold. It also maybe allows for some holes, which actually could be possible in certain situations. So the right question to ask here is, are the singular sets rectifiable, which is basically like manifold with holes, essentially. And the first real progress, so after Federer sort of did his work in the 60s on all this, the first really major progress on the structure of these things was due to Simon in the 90s. So some 30 years later. And what he proved was that for a minimizing harmonic map, F, so for minimizing, and if this target space is itself an analytic manifold, right? So the metric is analytic, the structure is analytic, not just smooth, but analytic. Then he was able to prove that this top stratum of the singular set for a minimizer, right, this n-3 part, is n-3 rectifiable. So he was able to show that it basically looks like a manifold, an n-3 manifold away from something that's smaller dimensional. By the way, to prove this, he introduced something called an infinite dimensional version of the Loja-Savich inequality. It was really a great breakthrough. Now, what's left with that, though, is basically asking, what about everything else? I mean, what about the stationary case? Well, what about the context for other stratums here? You should actually expect maybe all these things to have manifold structures, not just sort of the top piece. And then so after Simon's result, I guess maybe about 25 years later, Daniele and I proved sort of the general case. So we showed the following. So take a mapping F, which is a stationary harmonic map, so just a critical point of the energy functional between two Riemannian manifolds. Then no real assumptions on the manifolds here. Then every stratum of the singular set, Sk, is K rectifiable. So that is to say, basically looks like a K manifold away from a set of measure 0. And the idea, so I'm not going to maybe go into the proof here so that I have time to talk about defect measures a little bit, but maybe the one thing I'll mention is that, the ideas here for building structure for these things, in fact, all ideas I think that came before this, were built on basically strong methods. Using that you solved an equation in order to force rigidities of a scenario. And our methods, one of the reasons it's able to work for stationary guys in this context, and so generally, is that it basically only requires the monotone quantity. It uses almost nothing. It's a weak method. And as such, it's sort of been used by other people in a bunch of areas. So the exact same idea basically works with some various complications that arise for each sort of scenario. But for minimal surfaces, Yang-Mills free boundary problems, biharmonic maps, Ricci curvature, so forth and so on. Right? So these sorts of ideas are actually pretty general to build manifold structures on singular sets. And maybe one last point to sort of mention here is that, what, I'm going to not even mention. I'm going to skip past all this. I'm going to leave that be, because we're going to go to defect measure so that we have time to actually state something new. So that's from 2017. So basically, in the minimizing case, you can use to prove effective estimates on solutions. And this is actually kind of interesting because they're the first and still only effective estimates that are really proved for minimizers. Using these sorts of ideas to prove effective estimates are still basically the only real way to do it. Boom. So what I'm going to do here is I'm going to skip ahead now. We're going to start talking about defect measures. So defect measures are basically another way a singularity can arise so we've been talking about nonlinear harmonic maps, and we've been talking about the singularities of a fixed nonlinear harmonic map. But we can now sort of move our attention toward another form of singularity that can occur, which basically comes from sequences of harmonic maps. And the reason basically being, and this is sort of related to this codimension 3 conjecture at the beginning, is that even if you happen to be smooth away from a certain set, it turns out that in the stationary case, you aren't uniformly smooth. There can be blow up occurring as you're moving along in a sequence on a bigger set than you may be smooth on. And the defect measure is what's going to capture that. So in general, what you do now in this setup is you consider sequences of stationary harmonic maps, nonlinear harmonic maps. And they should all have, say, uniformly bounded energy along the sequence. And you want to ask what's blowing up as you sort of move along. So, even if the base manifold M here is a two-dimensional surface, so at this point, people can prove these mappings are smooth. Like all harmonic maps from surfaces into other spaces happen to be smooth. But if you take a sequence, there can be blowup occurring at a finite number of points. So this is codimension 2 along the sequence. And it's probably very instructive for us to actually consider an example of this real quick. I'll try to draw a picture, but maybe I'll draw a picture after everything gets said, because otherwise it'll get erased when I move to the next slide. So the idea is the following. So we're gonna be looking at a map in just a minute from basically R2 into S2, which I'm going to be viewing as a mapping from C into the complex projective space, CP1. So we can identify S2 with the complex projective space. This gives us some nice coordinates, basically, right? So it means that we look at pairs of complex numbers, Z1 and Z2, and we call a pair, we have an equivalence relation that says that two pairs are the same if when you can multiply them by some fixed complex number lambda, they only differ by that, right? So equivalently, it's the set of all complex planes inside of C2. And this is identified with S2. And our sequence of harmonic maps is going to be the following. For each epsilon, I'm going to look at a mapping from C into S2. And what it's going to do, so I think I lied, I'm going to draw a picture now just because otherwise it becomes too complicated. So here's my C. Here's my mapping of epsilon. Here's my radius epsilon here. And here's my S2. There you go. Then what this mapping basically does is it wraps C around S2 as sort of a diffeomorphism. The point at infinity of C here basically maps to one of the poles here. So at infinity, you're kind of converging to that guy there. And then most of the wrapping of this mapping is taking place inside of epsilon. So that this radius epsilon here is actually mapping onto most of the sphere, right? And then outside this ball of radius epsilon, it looks like a constant because it's all very close to this. So you are basically moving everything away. So here's my ball of radius epsilon is getting mapped onto most of the sphere, right? And then everything else is there. So as epsilon goes to 0, it looks like this is converging to a constant map. For this sequence of maps that map C onto S2, right, but map, like the ball of radius epsilon onto most of it, independent of epsilon and all of this, the energy is actually a constant. It does it with the same amount of energy, right? So the squared here is very important in the definition of energy. Oh, I wrote a pi. I'm not actually sure that's right. I meant to actually check that factor. It's something. Whatever it is, it's a constant. So this sequence of harmonic maps here from C into S2, right, they're basically becoming a constant away from the origin. They're wrapping around S2 very quickly near the origin, but they're all doing it with the same amount of energy. And so in the limits, as epsilon goes to 0, we see that sort of pointwise away from the origin, it's mapping to a constant. This north pole of the two sphere, but it always has a definite amount of energy. So that little epsilon ball is containing a lot of movement inside of it. On the other hand, at the origin, it's always mapped to the opposite point of the sphere. So it moves from one side of the sphere to the other side of the sphere by the time you move all the way around, but it's doing it faster and faster. So by the time you reach epsilon away, you've already moved almost epsilon close to the other side of the sphere. Note, by the way, the natural gradient estimate you get for these guys is epsilon to the -2, because basically in distance epsilon, it's moved all the way around the sphere. So we see that all of these f sub epsilons, they're all smooth, right? And they actually converge to something smooth. They're converging to the constant map. But what they're not doing is converging smoothly, right? At the origin, there's blowup occurring. All that energy of this map is being compressed inside the origin where all the movement is going. So you've got smooth maps converging to a smooth map, but they're not converging smoothly, right? And this is going to be the essence of defect measure. And the way you precisely sort of understand this is through something called defect measure, which I'll define carefully now. So again, let's just take a sequence of harmonic maps, stationary harmonic maps, say with bounded energy. Let's look at their energy. So the gradient of f squared, but view it as a measure now, right? So instead of viewing this as a function, I'm going to view this as a measure, right? This is L2, so it could be viewed as a function, but I want to view it as a measure. The reason being is that you'll lose less information as a measure. That this concentration will survive the measure, but it may not survive as a function. Then what we're going to do is that after passing to a subsequence anyway, you can prove that you can take a limit. So this sequence of harmonic maps, they will converge to some limit mat f naught. It's kind of subtle. This may not actually be harmonic, but it will converge to a limit map. And the measures, the energy measures going on here, they will converge to some limit measure. And this measure will essentially have two components: the energy of the limit function itself and something else. And the something else is going to be the part of this measure actually that's singular with respect to the say, Lebesgue measure or something. And we call this singular part the defect measure, right? It's the part of the limit of the energies that doesn't correspond to the energy of the limits, right? There's extra energy from the sequence that doesn't get seen by the limit function, and that's what we call the defect. And this is really capturing for us where blowup is occurring. So in our last example from before, when we had our sequence of mappings from C into S2 that racked around faster and faster under balls of radius epsilon, what was happening, right, was that our F sub j's here, which think of epsilon j, F sub epsilon really, we're mapping to a constant map weakly inside of H1, right, because point-wise it occurred actually away from that. And the energy measures, well, this being a constant, there is no energy for that limit function. But the energy measures were fully concentrating at the origin, which is where all the wrapping around was occurring, and they limit to just the Dirac delta at the origin. Note, by the way, that in this last example we were just discussing, that this defect measure was concentrated at a single point inside of R2 or C, which you can call its codimension 2 set, right? And this is a general phenomena, and this is a result going back to Feng Lin that basically says this always happens. So what he was able to do is he was able to prove that for a sequence of stationary harmonic maps, this defect measure limit that you get new by considering where f is blowing up by looking at the limit of the energy measure is actually a -2 rectifiable. So what that means is that it's supported on a set which is n-2 dimensional, and that mu as a measure is actually just like integrating over that set. So that is, we can write this defect measure as the integration over an n-2 dimensional set, Hausdorff measure is what's being stuck there, of some function e of x. And this E of x is what we call the energy density at this point. So we've got blowup occurring on an n-2 dimensional set, and E of x is telling us how much energy got lost at these various points of the set, how much blowup is actually occurring. So S in our context is the blowup set, E of x is the energy density, which is telling us how much energy got lost at some point x and S. So it turns out something interesting happens here, right? So in our sort of toy model example from before, we'll be able to see this very easily. So where you've got this blow up, where you've got this defect measure, where the solution's actually blowing up along your sequence, at most of these points, and I'll make this precise in just a second, you can blow up along them and you see bubbles, energy bubbles. Right? So this is where the term bubbling kind of comes from. So that is when we have blowup occurring, if we take these points and start zooming up in the correct way, what you'll get out of this is basically just a two-dimensional solution, which you always call a bubble because it can actually be compactified to a harmonic map from S2. So corresponding with defect measure are bubbles, blowups. And the precise definition is the following. So take some sequence of maps from the ball into some space N. And let's let B be some mapping from Rm and to N. Then we call this B a bubble map if the following holds. If you can write it, your Rm as an Rm minus 2 cross R2, right? So that your mapping B doesn't depend on the first m minus 2 variable. So it's really just a two-dimensional map, right? You've ignored m minus 2 of the variables. And that two-dimensional map you have is a finite energy harmonic map. We call that a bubble. It's called a bubble, once again, because you can conformally compact R2 into S2, and it's still a harmonic map when it's finite energy. So it actually is like an S2 harmonic map into your space. So we call such a thing a bubble map. And likewise, right, we call some F, which is a mapping from Rm into our manifold M, a blow up at a point X. So view X as being on the support of the defect measure where the blow up is occurring. If there's a sequence of points converging to it and a sequence of radii, so remember we had these blow up maps. It said, look at these points, look at these radii, we scale them to a ball of radius 1, like microscope up on them. So we see what's happening to our mapping on those balls, such that these blow-ups, which I guess I put a tilde here, or a little hat for the blow-ups, that we get, so we define the blow-ups from before, we just sort of microscoped up on these points and balls, converge to F, right? The difference here between here and the last scenario, right, is that we have a sequence of maps, and these points X and radii change with the sequence, right? So that the sequence sort of isn't at a fixed point that where you're zooming up. It's converging to some point X and supposed to be blowing up the sequence along the set. And then we call F a blow up if it comes from a limit of such things. And for our last complicated definition of the talk, we call B a bubble at X, right? If for this sequence we have a point X inside here, if B is a bubble map, so it's really just a two-dimensional harmonic map, and it arises as a blow up at X, right? So under this sequence of harmonic maps, I've got a sequence of blow-ups occurring. It's going to converge to really just a two-dimensional harmonic map, right? M minus 2 variables will be ignored, and we'll call such a thing a bubble map at this. And this sounds like a random definition, except for the fact that what Lin proved was that at almost every point of the defect measure, these things exist, right? Actually, quite a few of them exist. Which sort of brings us to the energy identity. So first, let's look at all this complicated terminology and sort of our easy example of mapping from C into S2, where our F sub epsilon, remember, will map the ball of radius epsilon onto most of the S2. It's just sort of wrapping around faster and faster as epsilon gets small. So observe here, if we just take the origin, right? So this is where the blow-up was occurring for the sequence of maps. And we take R sub epsilon here, just B epsilon, exactly our sort of chosen radius. Then our rescaled map is actually independent of epsilon in this case, because the epsilon that was here, right, just gets basically rescaled to a 1 afterwards, right? So when we rescale our F epsilon, we actually just get a constant map. It doesn't depend on epsilon anymore. And it's C wrapping around S2 one time, basically. And so clearly there's a blow up here, right? Because in fact, not only do these converge, but they actually converge. I mean, they're already converged, even without taking the limits. And so we have associated to our sort of easy example where we were wrapping around faster and faster is a single bubble map. And that bubble map was like F sub 1, the original guy that kind of maps around S2 just once. So there exists a unique bubble at this sort of blow up point of the sequence. And let's observe something that sounds random, but isn't. So recall that our energy of these guys, which was always exactly 8 pi, again, the 8 pi might be wrong, I forget, and it converged to a Dirac delta of that energy, right? So this here, so here's our defect measure here, right? Our E of X in this case is just the 8 pi, right? And the integration along the codimension 2 sets now is just, Dirac delta, because it's a point at that guy. And the energy now, at that point, it's exactly the energy of this bubble that actually occurred. So we blew up at this point. we got this bubble that actually that came from blowing up, and the energy of that bubble was exactly the factor in front of this integration. And this turns out to basically not be an accident, right? And if in general we have a random defect measure, so the set S is the blow up point, the E of X by Fong-Wall-Lin is sort of what you're integrating over. It's the amount of energy lost inside the sequence of the blow up. Then associated to almost every point of this blow up set, there are a finite number of bubbles BA that you can always get. There's always at least one. And based on Uhlenbeck and Taub's kind of proof for holomorphic maps and surfaces, right, the conjecture became the following. So for almost every point of the support of the defect, so for almost every point where this defect measure has support, so where the blowup is occurring, the energy lost at that point from this sequence is exactly the sum of the energy bubbles at this point. So what the energy identity is predicting for us is that we should be able to guess exactly how much energy gets lost at a point in this sequence by looking at all bubbles and just adding them up. And then that should be all you have to do, right? And basically, Uhlenbeck and Taub's proved this for pseudo-holomorphic maps from surfaces. So some quick literature. So for mappings from surfaces, right? So all this really started, as I said already, by Uhlenbeck and Taub's, and the collection of estimates that they kind of proved throughout this, that show this energy identity. And this was actually kind of plays a role in things like Gromov-Witten theory. This is basically for the compactifications of these moduli spaces. It's making sure that you have all the right kind of energies of the various sets on the sides. For general stationary harmonic maps that aren't holomorphic, so holomorphic are like really, really nice ones. They saw first order equations of second. It was proved by Parker and Yost in 96. For general mappings, so Fong-Wall-Lin, back when he proved these bubbles actually exist almost everywhere, he proved the lower bound. He proved that the energy at each point is at least as much as the sum of the energy of these bubbles, right? You have to at least have at least that much energy, but a priori there might be more. What he did prove is that if the target was a sphere, then together with Tristan Riviera, they actually proved the result is correct. So when you map into spheres, they were able to show that the energy of every bubble is the energy lost at a point is exactly the sum of the bubble energies. And interestingly enough, the way they really went about all this actually was that they proved that for mappings into the sphere, you have an L1 Hessian bound. And they were more generally able to prove this energy identity is true whenever you had this L1 Hessian bound, which they conjectured to be true, this W21 bound. And so main theorem, which I'm clearly not going to have time to talk about proofs much at all. So quite recently, Danielle and I proved the following. So we proved the energy identity. So it says that take a sequence of stationary harmonic maps, right, with bounded energy. Consider the defect measure, which recall once again is if after passing to a subsequence, the energy measures should converge to the energy measure, the limit function, plus your defect, which is supported on a codimension 2 sets. So that's where the blow up of the sequence is actually occurring and doesn't survive for the limit. Then this defect measure, the energy lost at each point of it is exactly the sum of the energy of the bubbles that occur at this point for some finite collection of bubble maps. And it's, we actually just require C2 geometry on each. And I think this is probably a good time for me to stop because, I don't know, I have an hour left and whatever. Okay, thank you very much.
Thank you for the lecture. Is there any question? Oh, with the microphone? Yeah, sure. Give me 1 second to pick up the microphone. But let me start by asking, are you sure about the 8 pi?
No, not at all.
No, because that's probably the most important part of the lecture. So, you have to be sure. Next time, check it.
What I'm sure is that whatever it is, it replace 8 pi with the correct amount of energy in every single spot, and then it's true.
Okay, sounds good. So
I think I wrote it down as a placeholder and I meant to change it and forgot.
So basically, with another definition of pi, it works if you want.
Yeah, something like that.
Any question from the audience? 1 second.
I don't know if you can hear reasonably now.
I can.
Okay, so, well, first, thanks for the very beautiful talk. And I was wondering if this bubble theory has an analogous in the other settings where the stratification applies, like rich curvature and so on.
Yeah, that's a good question. So interestingly enough, each of these different setups have sort of different phenomena that occur for limits. So for minimal surfaces, it's multiplicity, as opposed to defect measure, which is similar but not quite the same. But for Yang-Mills, you have basically the exact same phenomena occurring. You have bubbles there are basically certain four-dimensional instantons that kind of occur when you blow up. And Daniele and I actually proved the energy identity for Yang-Mills 5 or 6 years ago. But the problem was that the proof there doesn't work at all for harmonic maps. It completely breaks down in every way. So it's true, you can do it, but it was actually, I mean, I don't want to call it much easier because it was hard, but it was hard in a very different way at the very least. Like it really required a different set of ideas entirely to prove it.
Okay, thanks.
Okay, then if there, oh yeah, sorry, Alessandro.
Just as a follow-up, what is the main difference between Yang-Mills and harmonic maps, which makes the argument so different?
Right. So the short answer to that is codimension 2 versus codimension 4 singularities. The more refined answer to that is sort of the following. One can prove sort of a superconvexity in the Yang-Mills case. And, hidden behind all of it is somehow the fact that if you look at a Green's function in dimension 3 or higher, it's got like polynomial growth, right, at a point. But in dimension 2, it's log growth. And so these superconvexities, it's not just that the proof doesn't work for harmonic maps, they're actually wrong for harmonic maps. So basically everything we prove for Yang-Mills there is actually wrong for harmonic maps. Interesting, we weren't sure of that for quite a while. It was clear the proof didn't work, but we weren't sure it was wrong for a while. But they're actually wrong. That log behavior of codimension 2 singularities actually kills all the ideas, interestingly enough.
Okay, thank you.
Okay. Somebody has the same question, so you can repeat the same answer if you want, but I guess it's not necessary. If there's no further question, then I think we can thank Aaron again. And we'll see you tomorrow for the other talk about your work in Milano.
Yes.
Thank you again.
Yes.
Bye, everyone.
Thank you, guys. Good.